So today we're going to start by finishing up our little math boot camp by talking about change of bases and bases in general. So it follows from the sort of last comment that we were making about diagonalization in unitary matrices. We say that the unitary, there is a unitary change of basis for a unitary transformation so that you could represent the matrix as a diagonal matrix. So that's kind of convenient because it's really easy to work with diagonal matrices. But I think that this concept of change of basis can be really confusing, and so it would be good to just get on the same page about bases in general and change of basis in particular. So if we imagine we have some kind of n dimensional vector space, we're going to call it V, and we have a linear transformation in V, so it takes V to V, then we can choose different bases for V. So we can, let's call one of them x, and x is just equal to some set of coordinates. And we can call a different basis, we can choose a different one. Let's call it y, and it's just equal to some other set of coordinates. And so with respect to x, the linear transformation has matrix AX, and with respect to y, the linear transformation has matrix AY. But they both do the same thing. They both implement the same linear transformation. If a vector V in our vector space V has one set of, our vector V in vector space V has one set of coordinates in X and a different set of coordinates in Y. And so the question is, how do we change from one set of coordinates for our vector V to the other, and what's the relationship between these two matrices? So this topic can be really confusing, and it can be really easy to get yourself twisted up in working with the wrong matrix or its inverse or something like that. And so if you start with the basic idea about what you're trying to represent, then the rest should take care of itself. So we're going to look at a really simple example to hopefully illustrate this point. So let's imagine I have a city block, and it's laid out in this really nice rectilinear pattern so that I can use basis vectors for this city block. I'm going to use basis vectors x1 equals 1, 0, and x2 equals 0, 2 to position ourselves. And so I've given these coordinates using the standard basis. And what's convenient about choosing this particular basis for this particular city is that now I can say, go north along x2 for 1 block, and turn right and go east along x1 for 2 blocks, and that gets you to the star. So in terms of the x basis, this star is at position 2x1 plus x2. So what's unusual, I guess, kind of, is that x1 and x2 are not the same length, but I can choose anything. And I did that on purpose because in my city, my blocks are different dimensions. They're rectangles instead of squares. So it's convenient to choose my basis with different lengths. Okay, but things don't work out so well if my city happens to be laid out at an angle instead of in a nice north, south, east, west orientation. And in general, cities are laid out based on random history and how they developed over time, and so it's not actually that typical, except in modern cities, for them to be laid out in a nice grid. So if we want to walk along one basis vector and then the other, in this city, we would have to walk through buildings. And so that's not very convenient. I can't tell you walk 2 blocks north and then walk 1 block east. So we need to change to another basis that's more suitable for what we're trying to accomplish here, which is navigating this city. So we want to find a new basis that makes computation and moving around easier to do. So let's choose a new basis, y1 and y2, that line up better with our new road layout. So our city and locations in the new coordinate system are shown here. And to get to the star, I can now just say walk square root of 2 blocks along y1. So that's like 1.4 blocks. Okay, so that's the idea behind bases and change of bases. Let's look at a real example. Okay, so here I have two bases identified. One set in red labeled X and another set in Y labeled in blue. So my X basis is also a unit basis. And so little x1 is equal to little e1, and that's just 1, 0. And little x2 is equal to little e2, and that's just 0, 1. And my second basis, I'm going to call it y. Little y1 is equal to 2, comma, minus 1. And little y2 is equal to 3, comma, 2. So if I want to move from y basis to e basis, all I need to do is define a change of basis matrix that takes me from one to the other. So to go from y to e, my change of basis matrix is 2, minus 1, 3, 2, because that is the basis of my second basis, and my first basis is a unit basis. And this works because of what I have shown down here. So if I take this change of basis matrix times the vector 1, 0, I get 2 minus 1. So I go from one to the other. All right, so I can also think about the inverse of my change of basis matrix. So instead of going from y to e, I wanted to go from e to y. I would just take the inverse of the y-e, of the ey, of the y, sorry. If I want ey, I'm going to take the inverse of the ye matrix. So that's written here. It's 2 sevenths, negative 3 sevenths, 1 seventh, 2 sevenths. So for 2 by 2 matrices, the inverses are very straightforward. It's just 1 over the determinant of the matrix times the transpose. So it's not always the case that we're moving between some weird basis y and identity unit basis e. Sometimes we'll be moving between two bases that don't have easy to work with numbers, but the important thing to remember is that you can always go from a representation under a basis x to one under y by going through the standard basis e as an intermediate step. So you can always step from e to y and then x to e, or from the inverse of y to e and then x to e to get from x to y. So the standard basis is your friend when you're doing change of basis, and your two bases are not the standard basis. All right, so Hermitian matrices. What are some useful properties of Hermitian matrices that we talked a little bit about this week, or that you might know about from other classes you've taken? So first of all, if I'm a real matrix, what does being Hermitian mean? So for a real matrix, what's kind of the equivalent? Yeah, symmetric. What's handy about symmetric matrices? you can diagonalize it, for sure. So that's also true for Hermitian matrices. So Hermitian matrices are always diagonalizable. Another useful thing about Hermitian matrices is that I add, subtract, multiply Hermitian matrices, I'm going to get another Hermitian matrix. Anything else? So you can generate a unique basis. And kind of related, they have real eigenvalues whose eigenvectors form a unitary basis. So what about unitary? So unitary matrices, they're square matrices of complex numbers where the inverse is equal to the conjugate transpose. So the product of a unitary matrix and its conjugate transpose is identical. What are some useful properties of being unitary? So they maintain their magnitude. They're square. They're non-singular, meaning their determinant is not equal to 0. They're invertible. They're diagonalizable. Lots of good things. So square. Similar to Hermitian matrices, when I add, subtract, or multiply unitary matrices, I get another unitary matrix. So what else about unitary matrices? What are some other important properties for working with or thinking about unitary matrices? So another thing that we saw is that the absolute value of the determinant of a unitary matrix is 1. Identity matrices are unitary matrices. The rows of unitary matrices form an orthonormal basis, and so do the columns. What else? The modulus of every eigenvalue in a unitary matrix is 1. And I think the most important thing for us is that 1-qubit gates are always represented by 2x2 unitary matrices. So maybe I didn't say it right. It's this. So what's cool when we think about qubit gates, single qubit gates, or any qubit gates, being unitary is that nature doesn't allow arbitrary state transformations to occur. So when we think about changes of state over time of a closed quantum mechanical system, they're caused by unitary transformations. And so these unitary transformations are represented by unitary matrices, and an important result of this is that any quantum transformation that we're going to talk about, set measurement, is reversible. Okay. So I thought we could spend a few minutes doing a few problems. So let's start with this one. So I want you guys to spend, I don't know, a couple minutes thinking about showing, you don't need to prove anything really, show that this matrix is unitary. All right, I just sped through that, so hopefully I got all the multiplication right. But yeah, so all we need to do to show that this matrix is unitary is show that the matrix times its adjoint or its conjugate transpose is equal to identity. So we can just go through and write down what the conjugate transpose is, multiply the two matrices, and see that it ends up being 1/4 times 4004, which is just 1001. Let's do another one for fun. All right, so let's show that the absolute value of the determinant of a unitary matrix P, where P is defined as this matrix here, is 1. So it's a simple 2x2 matrix, so not so hard to find the determinant. All right, so this one's pretty easy once the minus sign is there. Anyways, yeah, sorry, I was missing the minus sign at the beginning. So yeah, most of the matrices we're going to be working with moving forward are 2x2 matrices. When we do multi-cubic gates, we'll see 4x4 matrices, for example. But they don't get too much more complicated than the one I showed you on your quiz today. So they'll be pretty easy to work with.